Hello guys, welcome to my new video on how to code Stable Diffusion from scratch. And Stable Diffusion is a model that was introduced last year. I think most of you are already familiar with it, and we will be coding it from scratch using PyTorch only. And as usual, my video is going to be quite long because we will be coding from scratch, and at the same time I will be explaining each part that makes up Stable Diffusion. So as usual, let me introduce you what are the topics that we will discuss and what are the prerequisites for watching this video. So of course we will discuss Stable Diffusion because we are going to build it from scratch using only PyTorch, so no other libraries will be used except for the tokenizer. I will describe the maths of the diffusion models as defined in the DDPM paper, but I will simplify it as much as possible. I will show you how classifier-free guidance work, and of course we will also implement it, how the text-to-image works, image-to-image, and in painting. Of course, to have a very complete view of diffusion models, actually we should also introduce the score-based models and all the ODE and SDIF theoretical framework. But most people are not familiar with the ordinary differential equations or even stochastic differential equations. So I will not discuss these topics in this video, and I leave it for future videos. So anyway, we will have a complete copy of a Stable Diffusion with the we will be able to do generate images using the prompt, also condition on existing images, etc. But for example, the samplers based on the Euler method or Runge-Kutta method will not be built in this video. I will make a future video in which I describe these ones. What do I expect you to have as a prerequisite for watching this video? Well, first of all, it's good that if you have some notion of probability and statistics, so at least you know what is a Gaussian distribution, what is the conditional probability, the marginal probability, the likelihood, etc. Now, I don't expect you to have the mathematical formulation in your mind about these concepts, but at least the concepts behind them. So at least what do we mean by conditional probability, or what do we mean by marginal probability? Anyway, even if you are not very strong with mathematics, I will always give a non-mathematics intuition for most concepts. So even if you don't have this background, you will at least understand the concept behind this, some intuition behind this. And of course, I expect you to know Python and PyTorch, at least basic level, because we will be coding using Python and PyTorch. And then we will be using a lot the attention mechanism. So if you're not familiar with the transformer model, please watch my previous video on that on the attention and the transformer. And we will be also be using a lot of convolutions. So I don't expect you to know how mathematical the convolution layers work, but at least what they do on a practical level in a neural network. Anyway, I will also review this while coding. And because this is going to be a long video, I will first, because the Stable Diffusion and the diffusion models in general are quite complex from a mathematical point of view. So we cannot jump directly to the code without explaining what we are going to code and how it works. The first thing I will do is to give you some background knowledge from a mathematical point of view, but also from a conceptual point of view of how the diffusion models work and how Stable Diffusion works. And then we will build each part one by one. Of course, at the beginning, you will have a lot of ideas that are kind of confused because I will give you a lot of new concepts to grasp. And it's normal that you don't understand everything at the beginning. But don't worry, because while coding, I will repeat each concept more than once. So while coding, you will also get a practical knowledge of what each part is doing and how they interact with each other. So please don't be scared if you don't understand everything in the beginning part of this video. Later, when we start coding it, everything will make sense to you. But we need this initial part because otherwise we cannot just jump in the dark and start coding without knowing what we are going to code. So let's start our journey. So what is Stable Diffusion? Stable Diffusion is a model that was introduced in 2022, so last year, at the end of last year I remember, by Comfits group at the Ludwig Maximilian University in Munich, Germany. And it's open source. The pre-trained weights can be found on the internet. And it became very famous because people started doing a lot of stuff and building projects with them and products with them, with the Stable Diffusion. And one of the most simple use of Stable Diffusion is to do text to image. So given a prompt, we want to generate an image. We will also see how image to image works and also how inpainting works. Image to image means that you already have a picture, for example, of a dog, and you want to change it a little bit by using a prompt. For example, you want to ask the model to add the wings to the dog so that it looks like a flying dog. Or inpainting means that you remove some part of the image. For example, you can remove, I don't know, this part here, and you ask the model to replace it with some other part that makes sense, that is coherent with the image. And we will see also how this works. Let's jump into generative models, because diffusion models are generative models. But what is a generative model? Well, a generative model learns a probability distribution of the data such that we can then sample from the distribution to create new instances of the data. For example, if we have many pictures of cats or dogs or whatever we have, we can train a generative model on it, and then we can sample from this distribution to create new images of cats or dogs or whatever. And this is exactly what we do with Stable Diffusion. We actually have a lot of images, we train it on a massive amount of images, and then we sample from this distribution to generate new images that don't exist in our training set. But the question may arise in your mind is, why do we model data as distributions, as probability distributions? Well, let me give you an example. Imagine you are a criminal and you want to generate thousands of fake identities. Imagine we also live in a very simple world, and each fake identity is made up of variables representing the characteristic of a person, so age and height. Suppose we only have two variables that make up a person, so it's the age of the person and the height of the person. In my case, I will be using the centimeter for the height. I think the Americans can convert it to feet. And so how do we proceed if we are a criminal with this goal? Well, we can ask the statistics department of the government to give us some statistics about the age and the height of the population. This information you can easily find online, for example, and then we can sample from this distribution. For example, if we model the age of the population like a Gaussian with the mean of 40 and the variance of 30, okay, these numbers are made up, I don't know if they reflect the reality. And the height in centimeters is 120 as mean, and the variance is 100. We get these two distributions. Then we can sample from these two distributions to generate a fake identity. What does it mean to sample from a distribution? To sample from this kind of distribution means to throw a coin, a very special coin that has a very high chance of falling in this area, a lower chance of falling in this area, an even lower chance of falling in this area, and a very nearly zero chance of falling in this area. So imagine we flip this coin once for the age, for example, and it falls here. So it's quite probable, not very probable, but quite probable. So suppose the age is 3, and let me write. So the age, let's say, is 3, and then we toss again this coin, and the coin falls, let's say, here. So 100, let's say 30, height 130 centimeter. So as you can see, the combination of age and height is quite improbable in reality. I mean, no 3 years old is 1 meter and 30 centimeters high. I mean, at least not the ones I know. So this combination of age and height is very not plausible. So to produce plausible pairs, we actually need to model these two variables, so the age and height, not as independent variables and sample from each of them independently, but as a joint distribution. And usually we represent the joint distribution like this, where each combination of age and height has a probability score associated with it. And from this distribution, we only sample using one coin. And for example, this coin will have a very high probability, with very high chance will fall in this area, with less chance will fall in this area, and very close to zero chance of falling in this area. Suppose we throw the coin and it ends up in this area. To get the corresponding, suppose this is the age, and this is the height. To get the corresponding age and height, we just need to do like this, and suppose these are actually the real height and the real height. Now the numbers here are actually do not match, but you got the idea that to model something we need a joint distribution over all the variables, and this is actually what we do also with our images. With our images we create a very complex distribution in which, for example, each pixel is a distribution and the entirety of all the pixels are one big joint distribution. And once we have a joint distribution, we can do a lot of interesting things. For example, we can marginalize. So for example, imagine we have a joint distribution over the age and the height. So let's call the age X, and let's call the height, let's say Y. So if we have a joint distribution, which means having P of X and Y, which is defined for each combination of X and Y, we can always calculate P of X, so the probability of over the single variable, by marginalizing over the other, so as the integral of P of X and Y and dy. And this is how we marginalize, which means marginalizing over all the possible y that we can have. And then we can also calculate the probability, the conditional probability. For example, we can say that the probability, what is the probability of the age being, let's say, from 0 to 3, given that the height is more than 1 meter, so something like this. We can do this kind of queries by using the conditional probability. So this is actually what we do with the generative model. We model our data as a very big joint distribution. And then we learn the parameters of this distribution because it's very complex distribution. So we let the neural network learn the parameters of this distribution. And our goal, of course, is to learn this very complex distribution and then sample from it to generate new data. Just like the criminal before wanted to generate new fake identities by modeling the very complex distribution that represents the identity of a person. In our case, we will model our system as a joint distribution by including also some latent variables. So let me describe. As you probably are familiar with the diffusion models, we have two processes. One is called the forward process and one is called the reverse process. The forward process means that we have our initial image that we will call x0, so this here, and we add noise to it to get another image that is same as the previous one but with some noise on top of it. Then we take this image which has a little noise and we generate a new image that is same as the previous one but with even more noise. So as you can see, this one has even more noise, and so on, so on, so on, until we arrive to the last latent variable called zt, where t is equal to 1000, when it becomes completely noise, pure noise, like n01, actually n0i, because we are in the multivariate world. And our goal actually is to this process, this forward process is fixed. So we define how to build the noisified version of each image given the previous one. So we know how to add noise, and we have a specific formula, an analytical formula, on how to add noise to an image. The problem is we don't have the analytical formula to reverse this process. So we don't know how to take this one and just remove noise. There is no closed formula on how to do it. So we learn, we train a neural network to do this inverse process, to remove noise from something that has noise. And if you think about it, it is quite easy to add noise to something than it is to remove noise from something. That's why we are using a neural network for this purpose. Now we need to go inside, of course, of the math, because we will be using it not only to write the code, but also to write the sampler. And in the sampler, it's all about mathematics. And I will try to simplify it as much as possible, so don't be scared. So let's start. Okay, this is from the DDPM paper, so Denoising Diffusion Probabilistic Models from Ho in 2020. And here we have two processes. The first is the forward process, which means that given the original image, how can I generate the noisified version of this image at time step t? In this case, actually, this is the joint distribution. let's look at this one here. This means if I have the image at time step t minus 1, how can I get the next time step, so the more noisified version of this image? Well, we define it as a Gaussian distribution centered, so the mean centered on the previous one, and the variance defined by this beta parameter here. This beta parameter here is decided by us, and it means how much noise we want to add at every step of this noisification process. This is also known as the Markov chain of noisification, because each variable is conditioned on the previous one. So to get xt, we need to have xt minus 1. And as you can see from here, we start from some x0, we go to x1. Here I call it z1 to differentiate it, but x1 actually is equal to z1. So x0 is the original image, and all the next x are noisy versions, with xt being the most noisy. So this is called the Markov chain of noisification, and we can do it like this. So it's defined by us as a process, which is a series of Gaussians that add noise. There is an interesting formula here. This is a closed loop, closed formula to go from the original image to any image at time step t without calculating all the intermediate images, using this particular parameterization. So we can go from the image, original image, to the image at time step t by sampling from this distribution, by defining the distribution like this. So with this mean and with this variance. This mean here depends on a parameter alpha bar, which is actually depending on beta, so it's something that we know. There is nothing we have to learn. And also the variance actually depends on alpha, which is defined as in function of beta, so beta is also something we know, so there is no parameters to learn here. Now let's look at the reverse process. The reverse process means that we have something noisy and we want to get something less noisy, so we want to remove noise. And we also define it as a Gaussian with a mean mu theta and a variance sigma theta. Now, this mean and this variance are not known to us. We have to learn them, and we will use a neural network to learn these two parameters. Actually, the variance we will also set it at fixed. We will parameterize it in such a way that this variance actually is fixed. So we hypothesize we already know the variance, and we let the network learn only the mean of this distribution. So to rehearse, we have a forward process that adds noise, and we know everything about this process. We know how to add noise. We have a reverse process that we don't know how to denoise, so we let a network learn the parameters on how to denoise it. And okay, now that we have defined these two processes, how do we actually train a model to do it? Because as you remember, our initial goal is actually to learn a probability distribution over our data set, and so this quantity here. But unlike before, when we could marginalize, for example, in the case of the criminal who want to generate identities, we could marginalize over all the variables. Here we cannot marginalize, because we need to marginalize over x1, x2, xt, x4 up to xt, so over a lot of variables. And to calculate this integral means to calculate it over all the possible x1 and over all the possible x2, etc. So it's a very complex calculation that is computationally intractable, we say. It means that it's theoretically possible, but practically it will take forever. So we cannot use this route here. So what can we do? We want to learn this quantity here. So we want to learn the parameter theta of this to maximize the likelihood we can see here. What we did is we can define, we found a lower bound for this quantity here, so the likelihood, and this lower bound is called the elbow. And if we maximize the lower bound, it will also maximize the likelihood. So let me give you a parallel example on what it means to maximize the lower bound. For example, imagine you have a company and your company has some revenue. And usually the revenue is more than or equal to the sales of your company. So you have some revenue coming from sales, maybe you also have some revenue coming from interest that you get from your bank, etc. But we can for sure say that the revenue of your company is more than or equal to the sales of your company. So if you want to maximize your revenue, you can maximize your sales, for example, which is a lower bound over your revenue. So if we maximize the sales, we will also maximize the revenue. And this is the idea here. But how do we do it on a practical level? Well, this is the training code for the DDPM diffusion models as defined by the DDPM paper. And basically the idea is, after we get the elbow, we can parameterize the loss function as this, which says that we need to learn, we need to train a network called epsilon theta that, given a noisy image, so this formula here means the noisy image at time step t and the time step at which the noise was added, the network has to predict how much noise is in the image, the noisified image. And if we do gradient descent over this loss function here, we will maximize the elbow, and at the same time we will also maximize the log likelihood of our data. And this is how we train this kind of networks. Now I know that this is a lot of concept that you have to grasp, so don't worry. For now, just remember that there is a forward process and there is a reverse process. And to train this network to do the reverse process, we need to train a network to detect how much noise is in a noisified version of the image at time step t. Let me show you how do we, once we have this network that has already been trained, how do we actually sample to generate new data. So let's go here. Let's go here. So how do we generate new data? Suppose we already have a network that was trained for detecting how much noise is in there. And what we do is we start from complete noise, and then we ask the network to detect how much noise is in there. We remove this noise, and then we ask the network again how much noise is in there, and we remove it. And then we ask the network how much noise is there, okay, remove it. Then how much noise is here, okay, remove it, etc., until we reach this step. Then here we will have something new. So if we start from pure noise and we do this reverse process many times, we will end up with something new. And this is the idea behind this generative model. Now that we know how to generate new data starting from pure noise, we also want to be able to control this denoisification process, so we can generate images of something that we want. I mean, how can we tell the model to generate a picture of a cat or a picture of a dog or a picture of a house by starting from pure noise? Because as of now, by starting from pure noise and going keep denoising, we will generate a new image, of course, but it's not like we can control which new image will be generated. So we need to find a way to tell the model what we want in this generational process. And the idea is that we start from pure noise, and during this chain of removing noise, so denoisification, we introduce a signal, let's call it prompt, or can also be called the conditioning signal, or it can also be called the context. Anyway, they are the same concept, in which we influence the model into how to remove the noise so that the output will move towards what we want. To understand how this works, let's review again how the training of this kind of networks works, because this is very important for us to learn how the training of this kind of network goes, so that we can introduce the prompt. Let's go back. Okay, as I told you before, our final goal is to model a distribution theta, p of theta, such that we maximize the likelihood of our data. And to learn this distribution, we maximize the elbow, so the lower bound. But how do we maximize the elbow? We minimize this loss. Here. So by minimizing this loss, we maximize the elbow, which in turn learns this distribution here, because it's the this elbow here is the lower bound for the likelihood of our the data distribution here. And What is this loss function? Loss function here indicates that we need to create a model, epsilon theta, such that if we give this model a noisified image at a particular noise level, and we also tell him what noise level we included in this image, the network has to predict how much noise is there. So this epsilon is how much noise we have added. And this is, and we do gradient descent on this training loop. This way we will learn a distribution over our data. But as you can see, this distribution doesn't include anything that tells the model what is a cat or what is a dog or what is a house. The model is just learning how to generate pictures that make sense, that are similar to our initial training data. But they don't know what is the relationship between that picture and the prompt. So one idea could be, okay, can we learn a distribution or joint distribution over the our initial data, so all the images, and the conditioning signal, so the prompt. Well, this is also something that we don't want, because we want to actually learn this distribution so that we can sample and generate new data. We don't want to learn the joint distribution that will be too much influenced by the context, and the model may not learn the generative process of the data. So our final goal is always this one. But we also want to find somehow to condition this model into building something that we want. And the idea is that we modify this unit. So this model here, epsilon theta, will be built using, let me show you, this unit model here. This unit will receive as input an image that is noisified, so for example a cat, and with a particular noise level, and we also tell him what is the noise level that we added to this cat, and we give them both to the input of the unit, and the unit has to predict how much noise is there. This is the job of the unit. What if we introduce also the prompt signal here, so the conditioning signal here, so the prompt? This way, if we tell the model, can you remove noise from this image which has this quantity of noise, and I am also telling you that it's a cat, so the model has more information on how to remove the noise. Yes, the model can learn this way how to remove noise and building something that is more closer to the prompt. This will make the model conditioned. It means that it will act like a conditioned model. So we need to tell the model what is the condition that we want, so that the model can remove the noise in that particular way, moving the output towards that particular prompt. But at the same time, when we train the model, instead of only giving images along with the prompt, we can also sometimes, with a probability, let's say 50%, not give any prompt and let the model remove the noise without telling him anything about the prompt. So we just give him a bunch of 0 when we give him the input. This way the model will learn to act both as a conditioned model and also as a conditioned model. So the model will learn to pay attention to the prompt and also to not pay attention to the prompt. And what is the advantage of this? Is that we can, when we want to generate a new picture, we can do 2 steps. In the first one, suppose you want to generate a picture of a cat, we can do like this. Let me delete first of all. Okay, we can do the first step, so let's call it step 1. And we can start with pure noise, because as I told you before, to generate a new image, we start from pure noise. We indicate the model what is the noise level, so at the beginning it will be t equal to 1000, so maximum noise level. And we tell the model that we want a cat. We give this as input to the unit. The unit will predict some noise that we need to remove in order to move the image towards what we want as output, so a cat. And this is our output 1. Let's call it output 1. Then we do another step. So let me delete this one. Then we do another step. Let's call it step 2. And again, we give the same input noise as before, the same time step as the noise level, so it's the same noise with the same noise level, but we don't give any prompt. This way the model will build some output. Let's call it out2. which is how to remove the noise to generate something. We don't know what, but to generate something that belongs to our data distribution. And then we combine these two outputs in such a way that we can decide how much we want the output to be closer to the prompt or not. This is called classifier-free guidance. So this approach here is called classifier-free guidance. I will not tell you why it's called classifier-free guidance, because otherwise I need to introduce the classifier guidance, and to talk about the classifier guidance I need to introduce the score-based models to understand why it's called like this. But the idea is this, that we train a model that when we train it, sometimes we give it the prompt and sometimes we don't give it the prompt, so that the model learns to ignore the prompt but also to pay attention to the prompt. And when we sample from this model, we do two steps. First time we give him the prompt of what we want, and the second time we give the same noise but without the prompt of what we want. And then we combine the two output, conditioned and unconditioned, linearly with a weight that indicates how much we want the output to be closer to our condition, to our prompt. The higher this value, the more the output will resemble our prompt. The lower this value, the less it will resemble our prompt. And this is the idea behind classifier-free guidance. To give the prompt, actually we need to give some kind of embedding to the, so the model needs to understand this prompt. To understand the prompt, the model needs some kind of embedding. Embedding means that we need some vectors that represent the meaning of the prompt, and these embedding are extracted using the clip text encoder. So before talking about the text encoder, let's talk about Clip. So Clip was a model built by OpenAI that allowed to connect text with images. And the text, basically, they took a bunch of images. So for example, this picture and its description. Then they took another image along with its description. So the image 1 is associated with the text number 1, which is the description of the image 1. Then the image 2 has the description number 2. The image 3 has the text number 3, which is the description of the image 3, etc., etc. They built this matrix you can see here, which is made up of the dot products of the embedding of the first image multiplied with all the possible captions here. So the image 1 with the text 1, image 1 with the text 2, image 1 with the text 3, etc. Then image 2 with the text 1, image 2 with the text 2, etc. How they train it? Basically, we know that the correspondence between image and the text is on the diagonal, because the image 1 is associated with the text 1, image 2 is associated with the text 2, image 3 is associated with the text 3. So how they train it? Basically, they said they built a loss function that they want this diagonal to have the maximum value and all the other numbers here to be 0, because they are not matching, they are not the corresponding description of these images. In this way, the model learned how to combine the description of an image with the image itself. And what we do in Stable Diffusion is that we take this text encoder here, so only this part of this clip, to encode our prompt to get some embeddings, and these embeddings are then used as conditioning signal for our unit to denoise the image into what we want. Okay, there is another thing that we need to understand. So as I said before, we have a forward process that adds noise to the image. Then we have a reverse process that removes noise from the image, and this reverse process can be conditioned by using the classifier-free guidance. And this reverse process means that we need to do many steps of denoisification to arrive to the image, to the new image. And this also means that each of these steps involves going through the unit with a noisified image and getting as output the amount of noise present in this image. But if the image is very big, so suppose this image here is 512 multiplied by 512, it means every time on the unit we will have a very big matrix that needs to go through this unit. And this may be very slow. because it's a very big matrix of data that the unit has to work on. What if we could somehow compress this image into something smaller so that each step through the unit takes less time? Well, the idea is that yes, we can compress this image with something that is called the variational autoencoder. Let's see how the variational autoencoder works. Okay, the Stable Diffusion is actually known as the known as a latent diffusion model, because what we learn is not the data probability distribution px of our data, but we learn the latent representation of the data using a variational autoencoder. So basically we compress our data, so let's go back, we compress our data into something smaller, and then we learn the denoisification process using this compressed version of the data, not the original data. And then we can decompress it to build the original data. Let me show you actually how it works on a practical level. So imagine you have some data and you want to send it to your friend over the internet. What do? You can send the original file, or you can send the zipped file. So you can zip the file maybe with WinZip, for example, and then you send the file to your friend, and the friend can unzip it after receiving and rebuild the original data. This is exactly the job of the autoencoder. The autoencoder is a network that, given an image, for example, will, after passing through the encoder, will transform into a vector which has a dimension that is much smaller than the original image. And if we use this vector and run it through the decoder, it will build the original image back. And we can do it for many images, and each of them will have a representation in this. This is called a code corresponding to each image. Now, the problem with autoencoder is that the code learned by this model doesn't make any sense from a semantic point of view. So the code associated with the cat, for example, may be very similar to the code associated with pizza, for example, or the code associated with a building. So there is no semantic relationship between these codes. And to overcome this limitation of the autoencoder, we introduce the variational autoencoder, in which we learn to kind of compress the data, but at the same time, this data is distributed according to a multivariate distribution, which most of the times is a Gaussian. And we learn the mean and the sigma of this distribution, this very complex distribution here. And given the latent representation, we can always pass it through the decoder to rebuild the original data. And this is the idea that we use also in Stable Diffusion. Now we can finally combine all these things that we have seen together to see what is the architecture of the Stable Diffusion. So let's start with how the text-to-image works. Now imagine text-to-image basically works like this. Imagine you want to generate a picture of a dog with glasses. So you start, of course, with a prompt, a dog with glasses. And then what do? We sample some noise. Here, some noise from the N01. We encode it with our variational autoencoder. This will give us a latent representation of this noise. Let's call it Z. This is of course a pure noise, but has been compressed by the encoder. And then we send it to the unit. The goal of the unit is to detect how much noise is there. And also, because to the unit we also give the conditioning signal, the unit has to detect the noise, what noise we need to remove to make it into a picture that follows the prompt, so into a picture of a dog. So the unit, we pass it through the unit along with the time step, initial time step, so 1000, and the unit will detect at the output here how much noise is there. Our scheduler, we will see later what is the scheduler, will remove this noise and then send it again to the unit for the second step of denoisification. And again, we send the time step, which is in this case not 1000 but 980, for example, because we skip some steps. And then we denoise, we detect how much noise is there. The scheduler will remove this noise and again send it back, and we do many times we keep doing this denoisification for many steps until there is no more noise present in the image. And after we have finished this loop of steps, we get the output z prime, which is still a latent, because this unit only works with the latent representation of the data, not with the original data. We pass it through the decoder to obtain the output image. And this is why this is called a latent diffusion model, because the unit, so the denoisification process, always works with the latent representation of the data. And this is how we generate text to image. We can do the same thing for image to image. Image to image means that I have, for example, the picture of a dog, and I want to modify this image into something else by using a prompt. For example, I want the model to add glasses to this dog. So I can give the input image here, and then I say a dog with glasses, and hopefully the model will add glasses to this dog. How does it work? We encode the image with the encoder of the variational autoencoder, and we get the latent representation of our image. Then we add noise to this latent, because the unit, as we saw before, his job is to denoise an image. But of course, we need to have some noise to denoise. So we add noise to this image, and the amount of noise that we add to this image, so this starting image here, indicates how much freedom the unit has into building the output image, because the more noise we add, the more the unit has freedom to alter the image. But the less noise we add, the less freedom the model has to alter the image, because it cannot change radically if we start from pure noise, the unit can do anything it wants. But if we start with less noise, the unit is forced to modify just a little bit the output image. So the amount of noise that we start from indicates how much we want the model to pay attention to the initial image here. And then we give the prompt. For many steps, we keep denoising, and after there is no more noise, we take this latent representation, we pass it through the decoder, and we get the output image here. And this is how image to image works. Now let's go to the last part, which is how inpainting works. Inpainting works similar way to the image to image, but with a mask. So inpainting means, first of all, that we have an image and we want to cut some part of this image, for example, the legs of this dog, and we want the model to generate new legs for this dog that are maybe a little different. So as you can see, these feet here are a little different from the legs of the dog here. So what we do is we start from our initial image of the dog. We pass it through the encoder. It becomes a latent representation. We add some noise to this latent representation. We give some prompt to tell the model what we want the model to generate. So I just say a dog running because I want to generate new legs for this dog. And then we pass the noisified input to the unit. The unit will produce an output here for the first time step. But then, of course, nobody told the model to only predict this area. The model, of course, here at the output predicted and modified denoised all the image. But we take this output here and we remove, we don't care what the noise predicted for this area of the image, the area that we already know. We replace it with the image that we already know, and we pass it again through the unit. Basically what we do is at every step, at every output of the unit, we replace the areas that are already known with the areas of the original image. So basically to fool the model into believing that it was the model itself that came up with these details of the image, not us. So every time here in this area, before we send it back to the unit here we combine the output of the unit with the existing image by replacing whatever output the unit gave us for this area here with what is the original image, and then we give it back to the unit, and we keep doing it. This way the model will only be able to work on this area here, because this is the one we never replace in the output of the unit. And then after there is no more noise, we take the output, we send it to the decoder, and then it will build the image we can see here. Okay, this is how the Stable Diffusion works from an architecture point of view. I know it has been a long journey. I had to introduce many concepts, but it's very important that we know these concepts before we start building the unit, because the model. Otherwise, we don't even know how to start building the Stable Diffusion. Here we are finally coding our Stable Diffusion. And the first thing that we will code is the variational autoencoder, because it's external to the unit, so it's external to the diffusion model, so the one that will detect, will predict how much noise is present in the image. And let's review it actually. Let's review the architecture. And let me go to this slide here. Okay, oops. This one here. Okay, the first thing that we will build is this part here. The encoder and the decoder of our variational autoencoder. The job of the encoder and the decoder of the variational autoencoder is to encode an image or noise into a compressed version of the image or the noise itself, such that then we can take this latent and run it through the unit. And then after the last step of the noisification, we take this compressed version or latent and we pass it through the decoder to get the output image, not the original. And so the encoder, actually his job is to reduce the dimension of the data into a smaller data, into the data with a smaller dimension. And the idea is very similar to the one of the unit. So we start with a picture that is very big, and at each step there are multiple levels. We keep reducing the size of the image, but at the same time we keep increasing the features of the image. What does it mean? That initially each pixel of the image will be represented by 3 channels, so red, green and blue, RGB. At each step, by using convolutions, we will reduce the size of the image, but at the same time we will increase the number of features that are that each pixel represents. So each pixel will be represented not by 3 channels, but by more channels. This means that each pixel will actually capture more data of the area to which that pixel belongs, and this is thanks to the convolutions. But I will show you later with an animation. And so let's start building. The first thing we do is open Visual Studio, okay, and we create 3 folders. The first is called data, and later we download the pre-trained weights that you can also find on my GitHub. Another folder called images, in which we put images as input and output, and then another folder called SD, which is our model. Let's create 2 files, one called encoder.py and one called decoder.py. These are the encoder and the decoder of our variational autoencoder. Let's start with the encoder, and the encoder is quite simple. So let's start by importing torch and all the other stuff. Oops. Let me also select the interpreter. Okay. Then we need to import 2 other blocks that we will define later in the decoder. Let's call them for now port VAE attention block and VA residual block. For those who are familiar with the computer vision models, the residual block is very similar to the residual block that is used in the ResNet. So later you will see the structure, it's very similar. But if those who are not familiar, don't worry, I will explain it later. So let's start building this encoder. And this will inherit from the sequential module, which means basically our encoder is a sequence of modules, submodules. Okay, it's a sequence of submodules in which each module is something that reduces the dimension of the data, but at the same time increases its number of features. I will write the blocks one by one, and as soon as we encounter a block that we didn't define, we go to define it, and then we define also the shapes. So the first thing we do, just like in the unit, is we define a convolution 2D. And initially our image will have 3 channels, and we convert it to 128 channels with a kernel size of 3 and a padding of 1. For those who are not familiar with convolutions, let's go have a look at how convolutions work. Here we can see that a convolution, basically, it's a kernel, so it's made of a matrix of a size that we can decide, which is defined by the parameter kernel size, which is run through the image as in the following animation, so block by block, as you can see. And at each block, each of the pixel below the kernel is multiplied by the value of the kernel in that position. So in this, for example, this pixel here, which is in position, let's say this one here. So the first row and the first column is multiplied by this red value of the kernel. The second column, first row, is multiplied by the green value of the kernel, and then all of these multiplications are summed up to produce one output. So this output here comes from 4 multiplications that we do in this area, each one with the corresponding number of the kernel. This way, basically, by running this kernel through the image, we capture local informations about the image, and this pixel here combines somehow the information of 4 pixels, not only 1, and that's it. Then we can also increase the kernel size, for example, and the kernel size, increasing the kernel means that we capture more global information, so each pixel represents the information of more pixel from the original picture, so the output is smaller. And then we can introduce, for example, the stride, which means that we don't do it every successive pixel, but we skip some pixels, as you can see here. So we skip every second pixel here. And if the number is the kernel size is even and the input is size is odd, we will also never touch, for example, here the border, as you can see. We can also implement a dilation, which means that it becomes with the same kernel size, the information becomes even more global, because we don't watch consecutive pixel, but we skip some pixels, etc, etc. So the kernels, basically, the convolutions, allow us to capture information from a local area of the picture, of the image, and combine it using a kernel. And this is the idea behind convolutions. So this convolution here, for example, will start with our, okay, let's define some shapes. Our variational autoencoder, so the encoder of the variational autoencoder, will start with a batch size, and 3 channels. Let's define it as channel. Then the image will have a height and a width, which will be 512 by 512, as we will see later. And this convolution will convert it into batch size, 128 features with the same height and the same width. Why in this case the height and the width doesn't change? Because even if we have a kernel size of size 3, because we add padding, basically we add something to the right side, something to the top side, something to the bottom and the left of the image, so the image with the padding becomes bigger, but then the output of the convolution makes it smaller and matches the original size of the image. This is the reason we have the padding here. But we will see later that with the next blocks, the image size will start becoming smaller. The next block is called the residual block, and a residual block, which is from 28 channels to 128 channels. This is a combination, this residual block is a combination of convolutions and normalization. So it's just a bunch of convolutions that we will define later. And this one indicates how many input channels we have and how many output channels we have. And the residual block will not change the size of the image. So we define it So our input image is 128, so batch size 128, height and width, and it remains the same basically. Oops. Okay, we have another residual block with the same transformation. Then we have another convolution, and this time the convolution will change the size of the image, and we will see why. So we have a convolution 2D, 128 to 128, because the output channels of the last block is 128, so the input channel is 128, the output is 128. The kernel size is 3, the stride is 2, and the padding is 0. This will basically introduce kernel size 3, stride 2. Let's watch. So imagine the batch size is 6 by 6, kernel size is 3, stride is 2 without a dilation, and this is the output. Let me make it bigger. Okay, something. Yeah. So as you can see, with the stride of 2, need to make it. Okay, with the stride of 2 and the kernel size of 3, this is the behavior. So we skip every 2 pixels before calculating the output, and this makes the output smaller than the input because of this stride, and also because of the kernel size, and we don't have any padding. So this transformation here will have the following shapes. So we are starting from batch size 128, height, width, so the original height and the width of the input image, but this time it will become batch size 128, the height will become half, and the width will become half, etc. Then we have 2 more residual blocks with the same as before, but this time by increasing the number of features. And also here we don't increase any. Here, by increasing the feature means that we don't increase the size of the image, or we reduce the size of the image, we just increase the number of features. So this one becomes 256, and here we start from 256, and we remain 256. Now you may be confused of why we are doing all of this. Okay, the idea is we start with the initial image and we keep decreasing the size of the image. So later you will see that the image will become divided by 4, divided by 8, but at the same time we keep increasing the features. So each pixel represents more information, but the number of pixels is diminishing, is reducing at every step. So let's go forward. Then we have another convolution, and this time the size will become divided by 4, and the convolution is, let me copy this one, 256 by 256, because the previous output is 256, the kernel size is 3, the stride is 2, and the padding is 0. So just like before, also in this case the size of the image will become half of what is it now. So the image is already divided by 2, so it will become divided by 4 now. Then we have another residual block in which we increase the number of features, this time from 256 to 512. So we start from 256 and the image is divided by 4, and we go to 512 and the image size doesn't change. Then we have another one from 512 to 512. In this case, oops, we will see later what is the residual block, but the residual block you have to think of it as just a convolution with the normalization. We will see later. And this one is 512, and that goes into 512. And then we have another convolution that will make it even smaller. So let's copy this convolution here. This one will go from 512 to 512, the same kernel size and the same stride and the same padding as before, so the image will become even smaller. So our last dimension was this. Let me copy it. So we start with an image that is 512, 4 times smaller than the original image, and with the 4 times smaller width, it will become 8 times smaller. And that's it. And then we have residual blocks also here. We have 3 of them in this case. Let me copy 1, 2, 3. I just write the one for the last one. So anyway, the size, the shape changes. Here it doesn't change the shape of the image or the number of features. So here we are going from divide by 8 and 512 here 512, and we go to same dimension 512, divide by 8 and divide by 8. Then we have an attention block, and later we will see what is the attention block. Basically it will run a self attention over each pixel. So each pixel will become kind of, as you remember, that the attention is a way to relate tokens to each other in a sentence. So if we have an image made of pixels, the attention can be thought of as a sequence of pixels, and the attention as a way to relate the pixel to each other. So this is the goal of the attention block. And because this way each pixel is related to each other, is not independent from each other. Even if the convolution already actually relates close pixels to each other, but the attention will be a global. So even the last pixel can be related to the first pixel. This is the goal of the attention block. And also in this case, we don't reduce the size because the attention is the transformer's attention is a sequence-to-sequence model. So we don't reduce the size of the sequence, and the image remains the same. Finally, we have another residual block. Let's let me copy here. Also no change in shape or size of the image. Then we have a normalization, and we will see what is this normalization. It's the group normalization, which also doesn't change the size, just like any normalization, by the way, with the number of groups being 32 and the number of channels being 512 because it's the number of features. Finally, we have an activation function called the CLU. The CLU is a function, it's derived from the sigmoid linear unit, and it's a function just like the ReLU. There is nothing special. They just saw that this one works better for this kind of application, but there is no particular reason to choose one over another, except that they saw that practically this one works fine for this kind of models. And if you watch my previous video about Llama, for example, in which we analyzed why they chose the Zwiglu function, if you read the paper, at the end of the paper they say that there is no particular reason they chose the Zwiglu. They just saw that practically it works better. I mean, it's very difficult to describe why a activation function works better than the others. So this is why they use the CLU here, because practically it works well. Now we have another 2 convolutions, and then we are done with the encoder. Convolution 512, 8, kernel size, and then padding. This will not change the size of the model, because just like before, we have the kernel size as 3, but we have the padding that compensates for the reduction given by the kernel size, but we are decreasing the number of features. And this is the bottleneck of the encoder, and I will show you later on the architecture what is the bottleneck. And finally, we have another convolution, which is 8 by 8 with kernel size equal to 1 and the padding is equal to 0, which also doesn't change the size of the image, because if you watch here, if you have a kernel size of 1, it means that each without stride, each kernel basically is running over each pixel, so each output actually captures the information of only 1 pixel, so the output has the same dimension as the input. And this is why here also we don't change the but here we need to change the number of it becomes 8, and here from 8 to 8. And this is the list of modules that will make up our encoder. Before building the residual block and the attention block, so this attention block, let's write the forward method and then we build the residual block. So this is the init, define it like this. Let me review it if it's correct. Okay, yeah. Now let's define the forward method. X is the image for which we want that we want to encode, so it's a tensor, torch.tensor. And the noise, we need some noise, and later I will show you why we need some noise that has the same size as the output of the encoder. This returns a tensor. Okay, our input x will be of size batch size with some channels. Initially it will be 3 because it's an image. Height and width, which will be 512 by 512, and then some noise. This noise has the same size as the output of the encoder, and we will see that it's actually batch size, then output channels, height divided by 8, and width divided by 8. Then we just run sequentially all of these modules. And then there is one little thing here that in the convolutions that have the stride, we need to apply a special padding, and I will show you why and how it works. So if the module has a stride attribute and it's equal to 2, which basically means this convolution here, this convolution here, and this convolution here, we don't apply the padding here because the padding here is applied to the top of the image, bottom, left, and right. But we want to do an asymmetrical padding, so we do it manually. And this is applied like this: f.padding. Basically, this says, can you add a layer of pixels on the right side of the image and on the bottom side of the image only? Because when you apply the padding, it's padding left, padding right, padding top, padding bottom. This means add a layer of pixels in the right side of the image and on the top side of the image, and this is asymmetrical padding. And then if it's we apply it only for these convolutions that have the stride equal to 2, and then we x is equal to module of x. Okay, now you may be wondering, why are we building this kind of structure? Why it's made like this? Okay. Usually in deep learning communities, especially during research, we don't reinvent the wheel every time. So the people who made the stable diffusion, but also the people before them, every time we want to use a model, we check what models similar to the one we want to build are already out there and they are working fine. So very probably the people who built stable diffusion, they saw that a model like this is working very well for some previous project as a variational autoencoder. They just modified it a little bit and kept it like it. So for most choices, actually there is no reason, there is a historical reason, because it worked well in practice. And we know that convolutions work well in practice for image segmentation, for example, or anything related to computer vision. And this is why they made the model like this. So most encoders actually work like this, that we reduce the size of the image, but we keep increasing the features of the image, the channels, the number of channels of the image. So the number of pixels becomes smaller, but each pixel is represented by more than 3 channels, so more channels at every step. Now, what we do is, here we are running our image into sequentially in one by one through all of these modules here. So first through this convolution, then through this residual block, which is also some convolutions, then this residual block, then again convolution until we run it through this attention block, and etc. This will transform the image into something smaller, so a compressed version of the image. But as I showed you before, this is not an autoencoder. This is a variational autoencoder. So the variational autoencoder, let me show you again the picture. Here, we are not learning how to compress data. We are learning a latent space, and this latent space are the parameters of a multivariate Gaussian distribution. So actually, the variational autoencoder is trained to learn the mu and the sigma, so the mean and the variance of this distribution. And this is actually what we will get from the output of this variational autoencoder, not directly the compressed image. And if this is not clear, guys, I made a previous video about the variational autoencoder, in which I show you also why the history of why we do it like this, all the reparameterization trick, etc. But for now, just remember that this is not just a compressed version of the image, it's actually a distribution. And then we can sample from this distribution, and I will show you how. So the output of the variational autoencoder is actually the mean and the variance. And actually, it's actually not the variance, but the log variance. So the mean and the log variance is equal to torch.chunk x2 dimension equal 1. We will see also what is the chunk function. So I will show you. So this basically converts batch size, 8 channels, height divided by 8 with divided by 8, which is the output of the last layer of this encoder, so this one. And we divide it into 2 tensors, so this chunk basically means divide it into 2 tensors along this dimension. So along this dimension it will become 2 tensors of size, along this dimension of size 4. So 2 tensors of shape, batch size 4, then height divided by 8, and width divided by 8. And this basically the output of this actually represents the mean and the variance. And what we do, we don't want the log variance, we want the variance actually. So to transform the log variance into variance, we do the exponentiation. So the first thing actually we also need to do is to clamp this variance, because otherwise it will become very small. So clamping means that if the variance is too small or too big, we want it to become within some ranges that are acceptable for us. So this clamping function, log variance, tells the PyTorch that if the value is too small or too big, make it within this range. And this doesn't change the shape of the tensors, so this still remains this tensor here. And then we transform the log variance into variance, so the variance is equal to the log variance.exp, which means to make the exponential of this, so you delete the log and it becomes the variance. And this also doesn't change the size of the shape of the tensor. And then to calculate the standard deviation from the variance, as you know, the standard deviation is the square root of the variance. So standard deviation is the variance.sqrt. And also this doesn't change the size of the tensor. Okay. Now, What we want, as I told you before, this is a latent space. It's a multivariate Gaussian, which has its own mean and its own variance. And we know the mean and the variance, this mean and this variance. How do we convert? How do we sample from it? Well, what we can sample from is basically we can sample from n01. This is if we have a sample from n01, how do we convert it into a sample of a given mu, so a given mean and a given variance? This, as if you remember from probability and statistics, if you have a sample from n01, you can convert it into any other sample of a Gaussian with a given mean and a variance through this transformation. So if z, let's call it this one, z is equal to n01, we can transform into another n, let's call it x, through this transformation. X is equal to z, the mean of the new distribution plus the standard deviation of the new distribution multiplied by z. This is the transformation. This is the formula from probability and statistics. Basically means transform this distribution into this one that has this mean and this variance, which basically means sample from this distribution. This is why we are given also the noise as input, because the noise we want it to come from with a particular seed of the noise generator. So we ask it as an input and we sample from this distribution like this. X is equal to mean plus standard deviation multiplied by noise. Finally, there is also another step that we need to scale the output by a constant. This constant, I found it in the original repository, so I'm just writing it here without any explanation on why, because I also don't know. It's just a scaling constant that they use at the end. I don't know if it's there for historical reason because they use some previous model that had this constant, or they introduced it for some particular reason. But it's a constant that I saw it in the original repository. And actually, if you check the original parameters of the stable diffusion model, there is also this constant. So I'm also scaling the output by this constant. And then we return x. So now what we built so far, except that we didn't build the residual block and the attention block here, we built the encoder part of the variational autoencoder and also the sampling part. So we take the image, we run it through the encoder, it becomes very small, it will tell us the mean and the variance, and then we sample from that distribution given the mean and the variance. Now we need to build the decoder along with the residual block and the attention block. And what we will see is that in the decoder we do the opposite of what we did in the encoder. So we will reduce the number of channels and at the same time we will increase the size of the image. So let's go to the decoder. Let me review if everything is fine. Looks like it is. So let's go to the decoder. Again, import torch. We also need to define the attention. We need to define the self-attention. Later we define it. Let's define first the residual block, the one we defined before, so that you understand what is this residual block. And then we define the attention block that we defined before, and finally we build the attention. So okay, this is made up of normalization and convolutions, like I said before. There is a two normalization, which is the group norm 1. And then there is another group normalization. is from out channels to out channels. And then we have a skip connection. Skip connection basically means that you take the input, you skip some layers, and then you connect it with the output of the last layer. And we also need this residual connection. If the two channels are different, we need to create another intermediate layer. Now I create it, later I explain it. Okay, let's create the forward method. Which is a torch.tensor and returns a torch.tensor. Okay, the input of this residual layer, as you saw before, is something that has a batch with some channels and then height and width, which can be different. It's not always the same. Sometimes it's 512 by 512, sometimes it's half of that, sometimes it's 1/4 of that, etc. So suppose it's x is batch size in channels, height, width. What we do is we create the skip connection. So we save the initial input, we call it a residual, or residue is equal to x. We apply the normalization, the first one, and this doesn't change the shape of the tensor. The normalization doesn't change. Then we apply the silo function, and this also doesn't change the size of the tensor. Then we apply the first convolution, this also doesn't change the size of the tensor, because as you can see here, we have kernel size 3, yes, but with a padding of 1. With a padding of 1, actually it will not change the size of the tensor. So it will still remain this one. Then we apply again the group normalization 2. This again doesn't change the size of the tensor. Then we apply the silo again. Then we apply the convolution number 2. And finally we apply the residual connection, which basically means that we take x plus the residual. But if the number of output channels is not equal to the input channels, you cannot add this one with this one, because this dimension will not match between the two. So what we do, we create this layer here to convert the input channels to the output channels of x, such that this sum can be done. So what we do is we apply this residual layer of residual, like this. And this is our residual block. So as I told you, it's just a bunch of convolutions and group normalization. And for those who are familiar with computer vision models, especially in ResNet, we use a lot of it. It's a very common block. Let's go build the attention block that we used also before in the encoder, this one here. And to define the attention, we also need to define the self-attention. So let's first build the attention block, which is using the variation autoencoder, and then we define what is this self-attention. It has a group normalization. Again, the channel is always 32 here in Stable Diffusion. But you also may be wondering, what is group normalization, right? So let's go to review it, actually, since we are here. And okay, if you remember from my previous slides on Llama, let's go here. When we use where we use a layer normalization, and Also in the vanilla transformer, actually we use layer normalization. So first of all, what is normalization? Normalization is basically when we have a deep neural network, each layer of the network produces some output that is fed to the next layer. Now what happens is that if the output of a layer is varying in distribution, so sometimes, for example, the output of a layer is between 0 and 1, but the next step maybe it's between 3 and 5, and at the next step maybe it's between 10 and 15, etc. So the distribution of the output of a layer changes, then the next layer also will see some input that it's very different from what the layer is used to see. This will basically push the output of the next layer into a new distribution itself, which in turn will push the loss function into basically the output of the model to oscillate between to change very frequently in distribution. So sometimes it will be very big number, sometimes it will be a very small number, sometimes it will be negative, sometimes it will be positive, etc. And this basically makes the loss function oscillate too much, and it makes the training slower. So what we do is we normalize the values before feeding them into layers, such that each layer always see the same distribution of the data. So it will always see numbers that are distributed around 0 with a variance of 1. And this is the job of the layer normalization. So imagine you are a layer and you have some input, which is a batch of 10 items. Each item has some features, so feature 1, feature 2, feature 3. Layer normalization calculates a mean and the variance over these features here, so over this distribution here, and then normalizes this value according to this formula. So each value basically becomes distributed between 0 and 1. With batch normalization, we normalize by columns, so the statistics mean and sigma is calculated by columns. With layer normalization, it is calculated by rows, so each item independently from the others. With group normalization, on the other hand, it is like layer normalization, but not all of the features of the item, but grouped. So for example, imagine you have 4 features here. So here you have F1, F2, F3, F4. And you have 2 groups, then the first group will be F1 and F2, and the second group will be F3 and F4. So you will have 2 means and 2 variance, one for the first group, one for the second group. But why we use it like this? Why do we want to group this kind of features? Because these features actually, they come from convolutions. And as we saw before, let's go back to the website. Imagine you have a kernel of 5 here. Each output here actually comes from a local area of the image. So the 2 close features, for example, 2 things that are close to each other may be related to each other. So 2 things that are far from each other are not related to each other. This is why we can group, we can use group normalization in this case. Because closer features to each other will have kind of the same distribution, or we make them have the same distribution, and things that are far from each other may not. And this is the basic idea behind group normalization. But the whole idea behind the normalization is that we don't want these things to oscillate too much. Otherwise, the loss of function will oscillate and will make the training slower. With normalization, we make the training faster. So let's go back to coding. So we were coding the attention block. So now the attention block has this group normalization and also an attention, which is a self-attention. And later we define it. And channels, okay. This one have a forward method. Torch.tensor returns, of course, a torch.tensor. Okay, what is the input of this block? The input of this block is something, where is it? Here. Is something in the form of batch size, number of channels, height and width. But because it will be used in many positions, this attention block, we don't define a specific size. So we just say that X is something that is batch size, features or channels if you want, height and width. Again, we create a residual connection. And the first thing we do is we extract the shape. So n is the batch size, the number of channels, the height and the width is equal to x.shape. Then, as I told you before, we do the self-attention between all the pixels of this image. And I will show you how. this will transform this tensor here into this tensor here, height multiplied by width. So now we have a sequence where each item represents a pixel because we multiplied height by width. And then we transpose it, so put it back little before, transpose the -1 with -2. This will transform this shape into this shape. So we put back this one, so this one comes before and features becomes the last one, something like this. And okay, so as you can see from this tensor here, this is like when we do the attention in the transformer model. So in the transformer model we have a sequence of tokens, each token representing, for example, a word, and the attention basically calculates the attention between each token. So how do two tokens are related to each other? In this case, we can think of it as a sequence of pixels, each pixel with its own embedding, which is the features of that pixels, and we relate pixels to each other. And then we do the attention, which is a self-attention, in which self-attention means that the query key and values are the same input, and this doesn't change the shape. So this one remains the same. Then we transpose back and we do the inverse transformation. So because we put it in this form only to do the attention. So now we transpose. So we take this one and we convert it into features and then height and width. And then again we remove this multiplication by viewing again the tensor. So NCHW. So we go from here to here. Then we add the residual connection and we return X. That's it. The residual connection will not change the size of the input, and we return a tensor of this shape here. Let me check also the residual connection here is correct. Okay. Now with that have also built the attention block, let's build also the self-attention, since we are building the attentions. And the attentions, because we have two kinds of attention in the stable diffusion. One is called the self-attention and one is the cross-attention. And we need to build both. So let's go build it in a separate class called attention. And okay, so again import torch. Okay, I think you guys maybe want to review the attention before building it, so let's go review it. I have here open my slides from my video about the attention model for the transformer model. So the self-attention basically it's a way for especially in a language model, is a way for us to relate tokens to each other. So we start with a sequence of tokens, each one of them having an embedding of size D model, and we transform it into queries, key and values, in which query key and values in the self-attention are the same matrix, same sequence. We multiply them by WQ matrix, so WQ, WK and WV, which are parameter matrices. Then we split them along the D model dimension into number of heads, so we can specify how many heads we want. In our case, the one attention that we will do here is actually only one head. I will show you later. And then we calculate the attention for each of these heads. Then we combine back by concatenating these heads together. We multiply this output matrix of the concatenation with another matrix called WO, which is the output matrix. And then this is the output of the multi-head attention. If we have only one head instead of being a multi-head, then we will not do this splitting operation. We will just do this multiplication with the W and with the WO. And okay, this is how the self-attention works. So in the self-attention we have this query, key, and values coming from the same matrix input. And this is what we are going to build. So we have the number of heads, then we have the embedding. So what is the embedding of each token? But in our case, we are not talking about tokens, we will talk about pixels, and we can think that the number of channels of each pixel is the embedding of the pixel. So the embedding, just like in the original transformer, the embeddings are the kind of vectors that capture the meaning of the word. In this case, we have the channels. Each channel, each pixel represented by many channels that capture the information about that pixel. Here we have also the bias for the W matrices, which we don't have in the original transformer. Okay. Now let's define the W matrices. So WQ, WK, and WV. We will represent it as one big linear layer. Instead of representing it as 3 different matrices, it's possible. We just say that it's a big matrix 3 by D embedding. And the bias is if we want it. So in projection bias. So this stands for in projection, because it's the projection of the input before we apply the attention, and then there is auto projection, which is after we apply the attention. So the WO matrix. So as you remember here, the WO matrix is actually D model by D model. The input is also D model by D model. And this is exactly what we did. But we have 3 of them here, so it's 3 by D model. And then we save the number of heads. And then we save the dimension of each head. The dimension of each head basically means that if we have multi-head, each head will watch a part of the embedding of each token. So we need to save how much is this size. So the D model divided by the number of heads. Embedding divided by the number of heads. Let's implement the forward. We can also apply a mask. As you remember, the mask is a way to avoid relating tokens that one particular token with the tokens that come after it, but only with the token that come before it. And this is called the causal mask. If you really are not understanding what is happening here in the attention, I highly recommend you watch my previous video, because it's explained very well, and if you watch it will take not so much time, and I think you will learn a lot. So the first thing we do is extract the shape. Then we extract its size, sequence length, and the embedding is equal to input shape. Then we say that we will convert it into another shape that I will show you later why. This is called the interim shape, intermediate shape. Then we apply the query key and value. We apply the in projection, so the WQ, WK, and WV matrix to the input, and we convert it into query key and values. So query key and values are equal to, we multiply it, and then we divide it. So with chunk, as I showed you before, what is chunk? Basically, we will multiply the input with the big matrix that represent WQ, WK, and WK, but then we split it back into 3 smaller matrices. This is the same as applying 3 different projections instead of, it's the same as applying 3 separate in projections, but it's also possible to combine it in one big matrix. This what we will do. Basically, it will convert batch size sequence length dimension into batch size sequence length dimension multiplied by 3, and then by using chunk we split it along the last dimension into 3 different tensors of shape, batch size, sequence length and dimension. Okay, now we can split the query key and values in the number of heads according to the number of heads. This is why we built this shape, which means split the dimension, the last dimension, into n heads. And values v.view. Wonderful. This will convert. Okay, let's write it. Batch size sequence length dimension into batch size sequence length, then h, so the number of heads, and the dimension divided by the number of heads. So each head will watch the full sequence, but only a part of the embedding of each token, in this case pixel, and we'll watch this part of the head. So the full the dimension, the embedding divided by the number of heads, and then this will convert it, because we are also transposing. This will convert it into batch size, h sequence length, and then dimension h. So each head will watch all the sequence, but only a part of the embedding. We then calculate the attention, just like the formula. So query multiplied by the transpose of the keys. So is the query matrix multiplication with the transpose of the keys. This will return a matrix of size, batch size, and sequence length by sequence length. We can then apply the mask. As you remember, the mask is something that we apply when we calculate the attention. If we don't want two tokens to relate to each other, we basically substitute their value. In this matrix, we substitute the interaction with -infinity before applying the softmax, so that the softmax will make it 0. So this is what we are doing here. We first build the mask. This will create a causal mask, basically a mask where the upper triangle, so above the principal diagonal, is made up of ones, a lot of ones. And then we fill it up with -infinity. Masked, oops, not mask, but wait. Masked fill, but with mask, and we put -infinity, like this. As you remember, the formula of the transformer is a query multiplied by the transpose of the keys and then divided by the square root of the module. So this is what we will do now. So divided by the square root of the module, self.d head. And then we apply the softmax. We multiplied by the WO matrix. We transpose back, so we want to remove, now we want to remove the head dimension. So output is equal to, let me write some shapes. So what is this? This is equal to batch size, sequence by sequence, multiplied, so matrix multiplication with batch size, this will result into batch size h sequence length and dimension divided by h. This we then multiplied by the then transpose, and this will result into, so we start with this one, and it becomes, wait, I put too many parentheses here, batch size, sequence length, h and dimensions. Okay, then we can reshape, as the input like the initial shape, so this one, and then we apply the output projection, so we multiply it by the WO matrix, okay. This is the self-attention. Now let's go back to continue building the decoder. For now we have built the attention block and the residual block, but we need to build the decoder. And also this one is a sequence of modules that we will apply one after another. We start with the convolution just like before. Now I will not write again the shapes change, but you got the idea. In the encoder let me show you here. Here in the encoder we keep reducing the size of the image until it becomes small. In the decoder we need to return to the original size of the image. So we start with the latent dimension and we return to the original dimension of the image. Convolution. So we start with 4 channels and we output 4 channels. Then we have another convolution. We go to 500. Then we have a residual block, just like before. Then we have an attention block. Then we have a bunch of residual blocks, and we have 4 of them. Let me copy. Okay. Now the residual blocks, let me write some shapes here. Here we arrived to a situation in which we have batch size, we have 512 features, and the size of the image still didn't grow because we didn't have any convolution that will make it grow. This one of course will remain the same because it's a residual block, and etc. Now to increase the size of the image, so now the image is actually height divided by 8, which height, as you remember, is 512, the size of the image that we are working with. So this dimension here is a 64 by 64. How can we increase it? We use one module called upsample. The upsample, we have to think of it like when we resize an image. So imagine you have an image that is 64 by 64 and you want to transform it into 128 by 128. The upsample will do it just like when we resize an image. So it will replicate the pixels, will twice, so along the dimensions right and down, for example, twice, so that the total amount of pixels, the height and the width actually doubles. And this is the upsample. Basically, it will just replicates each pixel, so that by this scale factor along each dimension. So this one becomes batch size divided by 8 with divided by 8 becomes, as we see here, height divided by 4 and width divided by 4. Then we have a convolution, residual blocks. So we have convolutions, 2D, 512 to 512. Then we have residual blocks of 512 by 500, but in this case we have 3 of them, 2, 3. Then we have another upsample. This will again double the size of the image. So we have another one that will double the size of the image, and by a scale factor of 2. So now our image, which was divided by 4 with 512 channels, so let's write it like this, will become divided by 2 now. So it will double the size of the image. So now our image is 256 by 256. Then again we have a convolution. Oops. And then we have 3 residual blocks again. But this time we reduce the number of features. So 256, and then it's 256 to 256. Okay. Then we have another upsamplings, which will again double the size of the image. And this time we will go from divide by 2 to divide by 2 up to the original size. And because the number of channels has changed, we are not 512 anymore. Okay. And then we have another convolution, this case with 256, because it's the new number of features. Then we have another bunch of residual blocks that will decrease the number of features. So we go to 256 to 128. We have finally a group norm. 32 is the group size, so we group features in groups of 32 before calculating the mu and the sigma before normalizing. And we define the number of channels as 128, which is the number of features that we have. So this group normalization will divide these 128 features into groups of 32. Then we apply the CILU, and then we have a convolution, the final convolution, that will transform into an image with the 3 channels, so RGB, by applying these convolutions here, which doesn't change the size of the output. So we will go from an image that is batch size 128, height width, why height width? Because after the last upsampling we become of the original size, into an image with only 3 channels. And this is our decoder. Now we can write the forward method. I'm sorry if I'm putting a lot of spaces between here, but otherwise it's easy to get lost and not understand where we are. So here the input of the decoder is our latent, so it's batch size 4, height divided by 8, width divided by 8. As you remember here in the encoder, the last thing we do is be scaled by this constant, so we nullify this scaling, so we reverse this scaling to 1.5, and then we run it through the decoder. And then return x, which is batch size, 3, height and width. Let me also write the input of this decoder, which is this one. We already have it. Okay, this is our variational autoencoder. So far, let's go review. We are building our architecture of the Stable Diffusion. So far we have built the encoder and the decoder, but now we have to build the unit, and then we have to build the clip text encoder, and finally we have to build the pipeline that will connect all of these things. So it's going to be a long journey, but it's fun actually to build things, because you learn every detail of how they work. So the next thing that we are going to build is the text encoder. So this clip encoder here that will allow us to encode the prompt into embeddings that we can then feed to this unit model here. So let's build this clip encoder, and we will of course use a pre-trained version, so by downloading the vocabulary, and I will show you how it works. So let's start. We go to Visual Studio Code. We create a new file in st folder called clip.py, and here, and we start importing the usual stuff. And we also import self-attention because we will using it. So basically clip is a layer, is very similar to the encoder layer of the transformer. So as you remember the transformer, let me show you here. The transformer, this is the encoder layer of the transformer, is made of attention and then feed forwards. And there are many blocks like this, one after another, that are applied one after another. We also have something that tells the position of each token inside of the sentence, and we will also have something similar in clip. So we need to build something very similar to this one, and actually this is why, I mean, the transformer model was very successful, so that's why they use the same structure, of course, also for this purpose. And so let's go to build it. The first thing we will build, I will build first the skeleton of the model, and then we will build each block. So let's build clip. And this has some embeddings. The embeddings allow us to convert the tokens. So as you remember, when you have a sentence made up of text, first you convert it into numbers, where each number indicates the position of the token inside of the vocabulary, and then you convert it into embeddings, where each embedding represents a vector of size 512 in the original transformer, but here in clip the size is 768, and each vector represents kind of the meaning of the word or the token captures. So this is an embedding. And later we define it. We need the vocabulary size. The vocabulary size is 49408. I took it directly from the file. This is the embedding size, and the sequence length, the maximum sequence length that we can have, because we need to use the padding, is 77. Because we should use some configuration file to save, but because we will be using with the pre-trained Stable Diffusion model, the size are already fixed for us, but in the future I will refactor the code to add some configuration actually to make it more extensible. This is a list of layers. Each, we call it the clip layer. We have this 12, which indicates the number of head of the attention, of the multi-head attention, and then the embedding size, which is 768, and we have 12 of these layers. Then we have the layer normalization, layer norm, and we tell him how many features, so 768. And then we define the forward method. This is tensor, and this one returns float tensor. Why long tensor? Because the input IDs are usually numbers that indicate the position of each token inside of the vocabulary. Also, this concept, please, if it's not clear, we'll go watch my previous video about the transformer, because it's very clear there when we work with the textual models. Okay, first we convert each token into embeddings. And then, so what is the size here? We are going from batch size, sequence length, into batch size, sequence length, and dimension, where the dimension is 768. Then we apply one after another all the layers of this encoder, just like in the transformer model. And the last one, we apply the layer normalization. And finally we return the output, where the output is of course it's a sequence to sequence model, just like the transformer, so the input should match the shape of the input should match the shape of the output, so we always obtain sequence length by the model. Okay, now let's define these two blocks. The first one is the clip embedding, so let's go clip embedding. How much is the vocabulary size? What is the embedding size? And number of token. Okay, so the sequence length basically. And super. Okay, we define the embedding itself using nn.embedding, just like always. We need to tell him what is the number of embeddings, so the vocabulary size, and what is the dimension of each vector of the embedding token. Then we define some positional encoding. So now, as you remember, the positional encoding in the original transformer are given by sinusoidal functions, but here in clip they actually don't use them. They use some learned parameters. So they have these parameters that are learned by the model during training that tell the position of the token to the model. Tokens and embeddings like this. We apply them. So first we apply the embedding. So we go from batch size, sequence length, to batch size, sequence length, dimension. And then, just like in the original transformer, we add the positional encodings to each token. But in this case, as I told you, the positional embeddings are not fixed, like not sinusoidal functions, but they are learned by the model. So they are learned, and then later we will load these parameters when we load the model. And then we return this X. Then we have the clip layer, which is just like the layer of the transformer model, the encoder of the transformer model. So returns nothing actually, and this one is wrong in it. Okay, we have just like in the transformer block, we have the pre-norm, then we have the attention, then we have a post-norm, and then we have the feed forward. So layer normalization. Then we have the attention, which is a self-attention. Later we will build the cross-attention, and I will show you what is it. Then we have another layer normalization. Then we have two feed-forward layers. And finally, we have the forward method, finally. So this one takes tensor and returns a tensor. So let me write it, tensor. Okay. Just like the transformer model. Okay, let's go have a look. We have a bunch of residual connection, as you can see here. One residual connection here, one residual connection here. We have two normalization, one here, one here. The feed forward, as just like in the original transformer, we have two linear layers, and then we have this multi-head attention, which is actually a self-attention because it's the same input that becomes query, key, and values. So let's do it. The first residual connection, X. So what is the input of this forward method? It's a batch size, sequence length, demo, and the dimension of the embedding, which is 768. The first thing we do is we apply the self-attention, but before applying the self-attention, we apply the layer normalization. So layer norm 1, then we apply the attention, but with the causal mask. As you remember, here, self-attention, we have the causal mask, which basically means that every token cannot watch the next tokens, so cannot be related to future tokens, but only the one on the left of it. And this is what we want from a text model, actually. We don't want the one word to watch the words that come after it, but only the words that come before it. Then we do this residual connection. So now we are, now we are doing this connection here. Then we do the feed forward layer. Again, we have a residual connection. We apply the normalization. I'm not writing all the shapes. If you watch my code online, I have written all of them, but mostly to save time, because here we are already familiar with the structure of the transformer, hopefully. So I am not repeating all the shapes here. We apply the first linear of the feed forward. Then as activation function, we use the GLU function, and actually called the quick GLU function, which is defined like this: x multiplied by torch.sigmoid of 1.702 multiplied by x, and that's it. Should be like this. So this is called the quick GLU activation function. Also here, there is no justification on why we should use this one and not another one. They just saw that in practice this one works better for this kind of application, so that's why we are using this function here. So now, and then we apply the residual connection, and finally we return x. This is exactly like the feed forward layer of the transformer, except that in the transformer we don't have this activation function, but we have the relu function. And if you remember in Llama, we don't have the relu function, we have the zwiglu function. But here we are using the quick GLU function, which I actually am not so familiar with. But I think that it works good for this model, and they just kept it. So now we have built our text encoder here, clip, which is very small, as you can see. And our next thing to build is our unit. So we have built the variational autoencoder, the encoder part, and the decoder part. Now the next thing we have to build is this unit. As you remember, the unit is the network that will, given some noisified image and the amount, and we also indicated to the network what is the amount of noise that we added to this image. The model has to predict how much image the noise is there and how to remove it. And this unit is a bunch of convolutions that will reduce the size of the image, as you can see, with each step, but by increasing the number of features. So we reduce the size, but we increase exactly what we did in the encoder of the variational autoencoder. And then we do the reverse steps, just like we did with the decoder of the variational autoencoder. So now again we will work with some convolutions, with the residual blocks, with attentions, etc. The one big difference is that we need to tell our unit not only the image that is already not, so what is the image with noise, not only the amount of noise, so the time step at which this noise was added, but also the prompt, because as you remember, we need to also tell this unit what is our prompt, because we need to tell him how we want our output image to be. Because there are many ways to denoise the initial noise. So if we want the initial noise to become a dog, we need to tell him we want a dog. If we want the initial noise to become a cat, we need to tell him we want a cat. So the unit has to know what is the prompt, and also he has to relate this prompt with the rest of the information. And what is the best way to combine two different stuff? So for example, an image with a text, we will use what is called the cross attention. Cross attention basically allows us to calculate the attention between two sequences in which the query is the first sequence and the keys and the values are coming from another sequence. So let's go build it and let's see how this works. Now the first thing we will do is create a new class, new file here called diffusion, because this will be our diffusion model. And I think also here I will build from top down. So we first define the diffusion class and then we build each block one by one. Let's start by importing the usual libraries. So import torch. From torch. And then we import the attention, the self attention, but also we will need the cross attention, and later we will build it. Then let's create the class diffusion. The class diffusion is basically our unit. This is made of time embedding, so something that we will define it later, time embedding 320, which is the size of the time embedding. So because we need to give the unit not only the noisified image but also the time step at which it was noisified. So the unit needs some way to understand this time step. So this is why this time step, which is a number, will be converted into an embedding by using this particular module called the time embedding, and later we will see it. Then we build the unit, and then the output layer of the unit, and later we will see what is it, this output layer. Output layer. Later we will see how to build it. Let's do the forward. As you remember, the unit will receive the latent. So this Z, which is a latent, is the output of the variational autoencoder. So this latent, which is a torch.tensor. It will receive the context. What is the context? Is our prompt. which is also a torch.tensor, and it will receive the time at which this latent was noisified, which is also, I don't remember, I think it's a tensor also. Later I define it. Okay, yeah, it's tensor. Okay, let's define the sizes. So the latent here is batch size 4, because 4 is the output of the encoder, if you remember correctly. Here 4 closing, okay, width, and the width divided by 8. Then we have the context, which is our prompt, which we already converted with the clip encoder here, which will be batch size by sequence length by dimension, where the dimension is 768 like we defined before, and the time will be another, we will define it later how it's defined, how it's built, but it's each embedding, but it's a number with an embedding of size. It's a vector of size 320. The first thing we do is we convert this time into an embedding. And actually this time we will see later that it's actually just like the positional encoding of the transformer model. It's actually a number that is multiplied by sines and cosines, just like in the transformer. Because it's they saw that it works for the transformer, so we can also use the same positional encoding to convey the information of the time, which is actually kind of an information about position. So it tells the model at which step we arrived in the denoisification. So this one will convert a tensor of 1, 320 into a tensor of 1, 1280, 1000. The unit will convert our latent into another latent, so it will not change the size. Batch for height. This is the output of the variation autoencoder, which first becomes batch 320 features through this the unit. So oops. So why here we have more features than the starting? Because let's review here. As you can see, the last layer of the unit, actually we need to go back to the same number of features you can see here. So here we start, actually the dimensions here don't match what we will be using. So this is the original unit, but the one used by Stable Diffusion is a modified unit. So in the last, when we build the decoder will not build the final number of features that we need, which is 4, but we need an additional output layer to go back to the original size of features. And this is the job of this output layer. So later we will see when we build these layers. So output is equal to self.final. This one will go from this size here to back to the original size of the unit, because the unit, his job is to take in latents, predict how much noise is it, then take again the same latent, predict how much noise, we remove it, we remove the noise, then again we give another latent, we predict how much noise, we remove the noise, we give another latent, we predict the noise, we remove the noise, etc, etc, etc. So the output dimension must match the input dimension. And then we return the output, which is the latent, like this. Let's build first the time embedding. I think it's easy to build. So something that encodes information about the time step in which we are. Okay. It is made of 2 linear layers, so nothing fancy here. Linear 1. Which will map it to 4 by n embedding, and then linear 2, four by n embedding into 4 by n embedding. And now you understand why it becomes 1280, which is 4 times 320. This one returns torch.tensor. So the input size is 320. What we do is first we apply the first layer, linear 1. Then we apply the silo function. Then we apply again the second linear layer. And then we return it. Nothing special here. The output dimension is 1 by 1280. 280. Okay. The next thing we need to build is the unit. The unit will require many blocks. So let's first build the unit itself, and then we build each of the blocks that it will require. So class unit. As you can see, the unit is made up of one encoder branch. So this is like the encoder of the variational autoencoder. So things go down, so the image becomes smaller, but the channels keep increasing, the features keep increasing. Then we have this bottleneck layer here. It's called the bottleneck. And then we have a decoder part here. So it becomes original size. The image from the very small size becomes the original size. And then we have these skip connections between the encoder and the decoder. So the output of each layer of each step of the encoder is connected to the same step of the decoder on the other side. And you will see this one here. So we start building the left side, which is the encoders, which is a list of modules. And to build these encoders, we need to define a special layer, basically, that will apply. Okay, let's build it and then I will describe it. Switch sequential. And basically this sequence is a switch sequential. Given a list of layers, we'll apply them one by one. So we can think of it as a sequential, but it can recognize what are the parameters of each of them and will apply accordingly. So after I define it, it will be more clear. So first we have, just like before, a convolution, because we want to increase the number of channels. So as you can see at the beginning, we increase the number of channels of the image. Here it's 64, but we go directly to 320. And then we have another one of these switch sequentials, which is a unit residual block. We define it later, but it's very similar to the residual block that we built already for the variational autoencoder. And then we have an attention block, which is also very similar to the attention block that we built for the variational autoencoder. Then we have okay, I think it's better to build this switch sequential, otherwise we have too many. Yeah, let's build it. It's very simple. As you can see, it's a sequence that given x, so which is our latent, which is a torch.tensor, our context, so our prompt, and the time, which is also a tensor, we'll apply them one by one. But based on what they are. So if the layer is a unit attention block, for example, it will apply it like this. So layer of X and context. Why? Because this attention block basically will compute the cross attention between our latents and the prompt. This is why. This residual block will compute, will match our latent with its time step, and then if it's any other layer, we just apply it. And then we return, but after the for while. Yeah. So this is, now we understood this. We just need to define this residual block and this attention block. Then we have another sequential switch, this one here. So the code I'm writing actually is based on a repository upon which actually most of the code I wrote is based on, which is in turn based on another repository which was originally written for TensorFlow, if I remember correctly. So actually the code for Stable Diffusion, because it's a model that is built by Compwit's group at the LMU University, of course it cannot be different from that code. So most of the code are actually similar to each other. I mean, you cannot create the same model and change the code. Of course the code will be similar. So we again use this one, switch sequential. So here we are building the encoder side, so we are reducing the size of the image. Let me check where we are. So we have the residual block of 320 to 64, and then we have an attention block of 8 to 80. And this attention block takes the number of head. This 8 indicates the number of head, and this indicates the embedding size. We will see later how we transform this, the output of this, into a sequence so that we can run attention on it. Okay, we have this sequential, and then we have another one. Then we have another convolution. Let me just copy. Convolution of size from 640 to 640 channels, kernel size 3, stride 2, padding 1. Then we have another residual block that will again increase the features. So from 640 to 1280. And then we have an attention block of 8 heads and 160 is the embedding size. Then we have another residual block of 1 to 80 and 1 to 80 and 8 and 160. So as you can see, just like in the encoder of the variational autoencoder, we with these convolutions we keep decreasing the size of the image. So actually here we started with the latent representation, which was height divided by 8 and height divided by 8. So let me write some shapes here. At least you need to understand this size changes. So batch size for height divided by 8 and width divided by 8. When we apply this convolution, it will become divided by 16. So it will become divided by 16. So it will become a very small image. And after we apply the second one, it will become divided by 32. So here we start from 16. Here it will become divided by 32. So what does it mean divided by 32? That if the initial image was of size 512, the latent is of size 64 by 64. Then it becomes 32 by 32. Now it has become 16 by 16. And then we apply these residual connections. And then we apply another convolutional layer, which will reduce the size of the image further from 32 here, divide by 32 and divide by 32 to divide by 64. Every time we divided the size of the image by 2, and the number of features is 1280 1280. Then we have a unit residual block, so let me copy also this one. Of 1280 and 1280, and then we have a last one, which is another one of the same size. So now we have an image that is 64 divided by 64 and divided by 64, but with much more channels. I forgot to change the channel numbers here. So here is 1280 channels, and divide by 64, divide by 64s, and this one remains the same because the residual connections don't change the size. Here should be 1280 to 1280. Here should be 640 to 640, and here it should be 320 to 320. So as I said before, we keep reducing the size of the image, but we keep increasing this number of features of each pixel basically. Then we build the bottleneck, which is this part here of the unit. This is a sequence of a residual block, then we have the attention block, which will make a self-attention, sorry, not self-attention, cross-attention, and then we have another residual block. Then we have the decoder. So in the decoder we will do the opposite of what we did in the encoder. So we will reduce the number of features but increase the image size. Again, let's start with our beautiful switch sequential. So we have 2560 to 1280. Why here is 2560 even if after the bottleneck we have 1280? So we are talking about this part here. So after the input of the decoder, so this side here of the unit, is the output of the bottleneck. But the bottleneck is outputting 1280 features, while the encoder is expecting 2560, so double the amount. Why? Because we need to consider that we have this skip connection here. So this skip connection will double the amount at each layer here. And this is why the input we expect here is double the size of what is the output of the previous layer. Let me write some shapes also here. So batch size 2560. The image is very small, so height by and width divide by 64, and it will become division to tant. Okay. Then we apply another switch sequential of the same size. Then we apply another one with an upsample, just like we did in the variational autoencoder. So if you remember, in the variational autoencoder, to increase the size of the image, we do upsampling. And this is what we do exactly here. We do upsample. But this is not the upsample that we did exactly the same, but it's this, the concept is similar. And we will define it later also, this one. So we have another residual with attention. So we have a residual of 2000, and then we have an attention block. 8 by 160. Then we have again this one. Then we have another one with upsampling. So we have 90-20, and then we have an upsample. This one is small. So I know that I'm not writing all the shapes, but otherwise it's really tiring job and very long. So just remember that we are keep increasing the size of the image, but we will decrease the number of features. Later we will see that this number here will become very small, and the size of the image will become nearly to the normal. Then we have another one with attention. So as you can see, we are decreasing the features here. Then we have 8 by 80, and we are increasing also here the size. Then we have another one. And 880. Then we have another one with upsampling, so we increase the size of the image. So 960 to 640. 8 heads with the dimensions embedding size of 80, and the upsampling with 640 features. And then we have another residual block with attention. Then we have another one which is a 640, 320, 840, and finally the last one we have 640 by 320 and 8 and 40. This dimension here is the same that will be applied by is the output of the unit, as you can see here, this one here, and then we will give it to the final layer to build the original latent size. Okay, let's build all these blocks that we didn't build before. So first let's build the upsample. Let's build it here, which is exactly the same as the joule. Okay. We have this convolution. Without changing the number of features. And this is also doesn't change the size of the image actually. So we will go from batch